so we can do some stuff. And then also we need Genie. It is. It should be. I mean, I hit the button, so yeah. It says we're streaming. Yeah. Okay, so let's see. Let's go to last time we were talking let me get rid of this. I'm pretty sure I know what's going on with this limit thing that we ran into, but let me do some more experimenting and I'll be able to come up with a better explanation, but it may need to wait a few weeks before I give it to you because of some of the background, the technical stuff that we haven't talked about yet. So so give me some time on that. Okay, so last time what did we do? We looked at started talking about data types in C, conditionals in C, sort of compound conditional expressions. So what do you do if you have like, you know, you need to do logical and or something along those lines. For loops in C, while loops in C, and right. So the sort of usual things you would expect to have in any language, looping, conditionals, that sort of stuff. Okay, so let me start a new example here, and let me just save it first. And let's make let's see, there it is. New folder, so let's do functions, say. Oops. Everything. Yeah. Well, so the question was, what kind of things can you do in C? You know, people use Python for all kinds of things. Pretty much any video game that you guys have played is programmed in, if not C, a sort of derivative of C. So, for example, Unreal Engine and anything based on Unreal Engine is all C++. Anything based on Unity, Unity's written in C Sharp, which is you know, sort of a Microsoft's object-oriented, you know, extensions and stuff to C++. Yeah, so basically the sky's the limit, right? You can do anything you want with it. Yeah, most game engines are written in C or C++ or C Sharp or something because C is fast. And the reason it's so fast is because there's less abstraction between C and assembly, which is, of course, machine code. And if you have a pretty mature compiler that is good at optimizing for stuff, then it'll run fast once you compile it. So, I mean, for example, I was going to give a CS colloquium today, but we decided to wait a few weeks because we haven't advertised it at all. And we were hoping that maybe we could do pizza and stuff, but Feller is just, yeah. So how do you guys feel? Rippy's not happy. If anybody saw the Discord channel yesterday. Um, huh? My Discord channel. Oh, yeah. I should put a link on the main page. But you can join the Wabash College Discord hub, and then you'll see my server because I've linked it to there because that's what these hubs are for, right? Yeah. Well, so how do you guys feel about the 2 more weeks of mass things? I mean, basically, I think Rippy is, huh? You love it? Okay. Well, Rippy's feeling, and maybe you guys share some of this, and given that today's the first faculty meeting, I would kind of like to get a sense for the peanut gallery's thoughts here. But his sort of feeling is that like the carrot is perpetually 6 feet in front of him, and like every time we make a little progress, that carrot keeps on moving. So. Well, yes, because Merca. Um, anyway, that said, if any of you have not turned in your vaccine card thing, because I got the sense from Feller's email that that's one of the major holdups is that we just don't have data for a bunch of guys, and that makes us sad. And if I find out that any of you are on that list, then that stick and you are going to become very acquainted. Okay. Rippy. Yeah. So, all right. We love you, Rippy. But, all right. So, yeah, I'm not happy about it either, but c'est la vie. I mean, it could be worse, right? We could be sending people into lockdown like last year. Okay, so what did we talk about last time with in terms of C? We were talking about, well, we defined strings so that we could do some printing. We did integers. We could have done floats also while we were at it. But yeah, okay, so let's get some stuff going, and let's start talking about functions. Now, if we go back to our first thing here, right, in a sense, any C program is itself a function. Um, and usually it's of the form blah. It takes in nothing because it's just a routine, and it outputs the convention. You don't have to output anything, but the convention, at least with Linux, is that your program returns to the operating system an exit status code, where 0 is the convention for exit status code good, everything was fine, and then you could use other exit status codes basically to as debugging and error conditions. So if your program crashes in some certain spot, you could say, exit code 17 or whatever, I don't know, right? And then report that to the operating system, and that is certainly useful for, if you're writing a gigantic program like a video game or something, that might be really handy. For the small stuff that we're doing, it's really not relevant, but yeah. So anyway, that's the convention on the main routine, and basically every C program has to have a main routine. There are a few minor exceptions to that for things that use C. So for example, Arduino programming. Has anybody done any of that? Right. So on an Arduino, you don't usually have a main routine, you have a loop routine, but basically the same deal. Um, okay, so basically everything's got to have a main function, and functions sort of look like this. They can return an object, and they can take in an object or multiple objects. Okay, so let's just start writing a function, and of course I need to first define my main function, and let's just do something like whatever. Okay, nothing particularly special. Um, and if I want to make a function that, let's say, takes in a number and does something with it, for the sake of example, what's, because we're also going to talk about recursion today, what's everybody's favorite example of a recursively generated thing? Something that requires recursion. Hmm? I can't hear. The Fibonacci numbers? What's another good one? Huh? Oh, yeah, you could do that recursively. Yeah, that makes sense. Uh, maybe on the subject of that, raising things to bigger and bigger exponents, what's sort of another mathematical thing that's sort of like that? The factorial function. Okay. So we'll save, I'll give you guys the Fibonacci's as your assignment. And so we'll do the factorials as our example. Yeah, sound good? Okay, so first off, what is the factorial function, right? Yeah. Keep going. With 4 times 3, it's 4 times 3 times 2 times 1, right? By all the previous numbers until you hit 1, right? Now, obviously, you don't have to multiply by 1 because math, but, right? So what's 4 factorial? 24. Okay, and how did you compute that? Yeah, you did 4 times 3 times 2, and then, well, times 1, but okay. And 5 factorial would be 120 because it's 5 times 4 times 3 times 2 times 1 and so on. Okay, they are recursive in the sense that the fundamental identity for them is that, right? So that's sort of the recursive, but we can use this both as a recursive definition and as an iterative definition. That 5 factorial is 5 times whatever 4 factorial was. And if you already know what 4 factorial is, great. If you don't, well, what's 4 factorial? 4 times 3 factorial. Well, do you know what 3 factorial is? Maybe, maybe not. What's 3 factorial? 3 times 2 factorial. Well, what's 2 factorial? 2 times 1 factorial, and what is 1 factorial defined to be? 1, okay? So the chain sort of has to end eventually, okay? And the convention on factorials are, well, the fundamental definition, right? What's 1 factorial? What's 0 factorial? 1. The convention is 1, okay? Now, you might ask, why the hell 1? That doesn't make any sense. Okay, here's the way I like to think about it, other than it just makes things work correctly, all the formulas and stuff. If I have, let's say, well, okay, Thursday I'm flying to Texas. I'll be back Sunday night. Okay, so I need 4 shirts for the trip. What I'm wearing on Thursday, Friday, Saturday, and Sunday. Okay, let's say that I pack 4 shirts in the suitcase, right? How many different orderings are there for me to wear these 4 shirts? Well, on Thursday, how many choices of shirt do I have? 4. I haven't worn anything yet. Okay. And then on Friday, how many shirts do I have to pick from? 3. And then 2, and then 1. Okay. So the total number of arrangements for which order I wear all 4 shirts in is given by 4 factorial. Okay. 4 choices on the first day, 3 for the second, and so on, until I get to Sunday, in which case there's only 1 clean shirt, and that's the one I wear. What about if I have 0 shirts? How many ways are there for me to select my 0 shirts to wear? There's 1 way. I have nothing to wear. Okay. I know, it's still kind of stupid to say it that way, but do you guys get the idea? Right? Okay. So our base case here would be that 0 factorial is defined to be 1, and 1 factorial is defined to be 1. Okay. And then all the others are defined in terms of the previous ones. It is possible, by the way, to define this for non-integers. How many of you guys have taken differential equations? The old gamma function, yeah, is how you can do sort of non-integer factorials, sort of. And if you don't know what, if you haven't run into the gamma function yet, take differential equations because it's really cool, or not. Okay, so I want to write a function here and I'll call this one fact1 because it's going to be the factorial function done in one particular method, okay? And if I just do something stupid, oops, like misspell return, okay, I can define a new number as the result of passing some value or something to a function like so, okay? Oh, and I need to do ints, let me call this just x, okay? So what kind of object comes into this factorial function? An integer called x, okay? So if I wanted to do let me just do something silly like let's make the function do nothing but spit back what came in. Okay, not a very useful function, but for now it's fine. And so what will happen, I'll define the number num to be 4. I'll pass that to the factorial function. It becomes, in the formulas here, represented as x. Okay, what gets returned by the function? An integer, and what value in this case? Whatever x is, okay? And so in this case, it's the same as whatever came in. And so then this answer variable will just be the same number here, 4. And then I could, for example, print this. Like so. Okay, so here, and this is maybe slightly different than the print command that we used before, what we're providing the printf function is with a formatting string, and inside the formatting string, there's only one object here, a %i, which means what kind of data am I printing? An integer, okay? And which integer am I printing? The one called answer. So I could, for example, do something like the number is blah, something like this, in which case, how many times do I have a %i type thing there? Twice, okay? And so what I would have to do is give it the thing I want printed twice, and the things that go after your formatting string fill in the %whatevers in the order that they come in, right? So here I'm printing the same integer twice, but I could print like an integer and a float and a string, and I would put those in the order that they appear in the formatting string. Like the actual % symbol? No, you can. And of course, the trouble, right, is that you've got the % is used as part of formatting string. It is possible to print a % if you need to. So yeah, I'll show you guys that later. Okay, so let's compile and run this and see if it makes sense. All right, so what should happen when this is all done? What should print? The number is 4. I repeat, the number is 4. Okay. All right, so let's test that. And functions. Okay, so okay, I'm just going to go straight to a binary, not through assembly for right this instant, just for the sake of time. But there we go. Okay. All right, so does that make sense? Sort of? A little bit? Yeah. Okay. All right, so back to our function here. This function is useless because all it does is return what you gave it. Okay, so let's spice it up a bit and actually make it do something. Okay, and I want this thing to be computing the factorials. So what do we need to know about the factorial? Well, what happens if the factorial function is, well, let's say that I get the number 5 in. Then how do I compute 5 factorial? Using that, okay? So let's actually do it the recursive way first, okay? And so what I need to do is, well, if the input number is either 0 or 1, okay, what's the convention? What's 0 factorial? 1, and also 1 factorial is defined to be 1, okay? Okay, now 2 things here. One, what is the double vertical bars mean? It means logical OR, okay? And in of course Python, you just type the word OR, right? But this ain't Python. And then the second thing is here, x equals 0 or x equals 1. Why did I type two equal signs? Well, it is how you do it in Python. Okay, but what's the difference between single and double equals? Yeah, Farden. Right. So single equals is used for assigning a value to a variable. Double equals is testing, is the variable's value the same as whatever's on the other side of the double equals sign? Okay, so you can think maybe in a different way is that double equals is actually a function, right? That you give it two things and it's going to output either true or false, depending on whether or not those two things are equal or not, okay? And then the double vertical bars is a logical operation, okay? And logic operations can only operate on Boolean things, things that are true or false, okay? Now, in C, how are true and false represented? 0 and 1, how are they represented in Python? The word true and the word false, right? Okay, so anyway, you got to be careful with the double equal versus single equal. Okay, good on that? Yeah, okay. So in the situation where the input number is either 0 or 1, what should we return? 1. Okay, and in the situation where the number is something else, then what? Yeah, we got to do some math. All right. And what's going to be, if we think about this recursively, what am I going to type here? Hmm? Exactly. Okay. So what's the recursive definition? 5 factorial is 5 times whatever 4 factorial is. Okay. And so in terms of our function, that's our number x that we're dealing with times whatever fact of the previous number is. Okay. Fact 1, yes, because that's what we're defining. Oh, okay. The computer doesn't know that this is the factorial. All the computer knows is that I want to call the function fact, right? The fact that it generates the factorial function is because we know what the factorial function is. From the computer's perspective, all it's doing is saying, okay, well, I'm going to take x minus 1, I'm going to pass it to the factorial function, and whatever I get out, I'm going to multiply, put there. Okay, that's it, right? It doesn't care what's actually happening. Hmm? Yeah. Yeah. Well, this is a recursive function, right? And this is just how you do recursion, right? So what's the well? Let's have some fun with this. Well, there's a couple ways you can do this. Okay. All right. So this is DuckDuckGo, but let's say we go to Google, right? Let's Google recursion. Did you mean recursion? Well, yes, in fact I did. Oh, did I mean recursion? Did I mean recursion? Yeah. And of course, to understand recursion, you must first understand Recursion. Okay. Yeah, so what is recursion, right? Recursion is a self-referential definition, right? Here, the function fact1 is defined in terms of itself. And that's okay, provided that this recursion can't go on forever. Okay, and what I mean by that, well, okay, let's back up. Mathematically, recursion can go on forever. Okay, and in certain contexts in logic and stuff, that can happen. But on a computer, can recursion go on forever? No. Why? Well, there's only so much memory in any computer, right? You could throw more memory at a computer and extend the depth of the recursion a bunch, but eventually, no matter what, you're still going to run out of memory. No, but yeah. Download more memory. It doesn't work like that. Yeah. Eventually, no matter what, you still eventually will run out of memory. Okay. Well, the last time I checked, the universe is a finite object, so no. Hmm. Okay, I can guarantee you when I was 19, I was not checking whether or not the universe was finite. In fact, probably the opposite. There were probably a few evenings when I was 19 where I was very much convinced that the universe was infinite. Okay. That can I may have been chemically convinced of that, but whatever. Yeah. Well, go talk to Doc Brown. Okay. All right. Anyway, point being that from a computing standpoint, there has to be a limit to the recursion. Okay. And so how many of you guys, when you were in like high school, you had your TI graphing calculator and you put in to try and figure out what's the biggest numbers factorial that you can have the thing compute? Anybody do? This was all the rage when I was in school. Okay. Um, all right, fine, losers. Okay, so there we go. All right, so what should come out of this thing this time? Whatever 4 factorial is, which is 24. Okay. All right, well, first off, let's compile and run this thing and make sure that we haven't screwed anything up. Okay, it worked. Okay, so let's actually trace through how the heck we got 24. Okay, so to do this, I'm going to use an auxiliary program called GDB, okay, for GNU Debugger. Now, if I'm working in pure C, then it doesn't really matter what architecture I'm dealing with, okay? Whereas if, as we're going to find out when we really get into the weeds with assembly, probably what, next week or so, if you're on a ARM device, well, okay, GDB is like GCC in the sense that if you fire it up, it's going to assume that you're working within the target architecture or your host architecture, okay? So if you want to do cross-compiled stuff and also GDB with that, then you have to use multi-arch GDB, which is a whole other little ball of wax, and we'll deal with that later. Okay, for now, let's go in here. Okay, so I'm going to do break main and put in a breakpoint, and I'm going to step through this run first, and then oh, right, okay, hang on one second. Let me do one other thing here. Okay. So sometimes with GDB, you need to do static compiling or linking. and just don't worry about the details for right this instant. Okay, so what this is going to do is I'm going to step through line by line through this thing. Now, it's not particularly illuminating because the function is done, okay? This will be much more illuminating when we actually do the when we do this in assembly. Okay, so let me quit this and restart it. And instead of breaking on main, I'm going to break on fact1. Okay, and then I'm going to run the program. Oh, yeah. Oh, that's right. I'm sorry. I forgot one thing. Hold on. That's right. Okay, sorry, I forgot one thing. So what did I just do? If I want to do debugging, I forgot the debugging flag. There's sort of two things that I need to add to my GCC command. The first is I need to use the static linking. That's more so because I'm using the print function than any other specific reason. You'll get used to that later. And then the other thing is the -G, okay, for debugging. And so what this is going to do is generate basically debugging stuff to go with the executable, which means that when I go through and run this through GDB, we'll actually get some more illuminating stuff out of it. Okay, so yeah, the -G generates a bunch of debugging stuff. And in particular, what it does is it means that, so line 19, if you'll notice here in my file, right, line 19 is the first instruction in the main command or the main function routine, okay, to define that number equals 4. And by generating the debugging, what we can do is step literally line by line through the code and see what's happening. Okay. All right. Does that kind of make sense? Yeah. Okay. So let's continue stepping through it and see what happens. Okay. So step literally does one instruction. Okay. And so here, that's the instruction. And then, well, what does this instruction say to do? Pass this number 4, okay, to the fact function, okay? The fact function, what is the number that got passed to it called? We called it, within it, it's x, okay? And what's its value? 4, okay? And so, and now we're on line 6, which is back up here for the if condition, okay? So let's step again. All right, why did we go to this, to line number 12 next? Well, what's x? What's x? Yes, Farden. Right, x is 4. 4 is not equal to 0 and it's not equal to 1, okay? So the if condition here fails and we go to the else condition. What's inside the else part? To return what? X times the factorial of x minus 1, okay, which is the instruction we have there. Okay, so that's what will get executed next. Okay, so we good with this? Here's where it gets fun. Because down the rabbit hole we go. Now we're back here. But what's x this time? 3. Okay, because what did we pass to the fact function? We passed, well, we originally passed 4, but now what are we passing it? 3, okay, 1 fewer, all right? And then we just start over again at the top, right? Is 3 equal to 0 or 1? No, so we go to the else case. And what am I going to do now? But it'll be this time with x equals 2. X equals 1. Okay, return 1, curly brace, curly brace. Okay, why is it doing that? Oh, yeah, okay. Why did it do 4 sets of curly braces? Yes, exactly. We had to come back out of the rabbit hole. Okay. Huh? Well, sort of. Not up in the sense of the lines of code, up in the sense of the recursion. Okay. So what were we doing? We wanted to compute fact 1 of 4. Okay. And in order to do that, what did we have to do? We had to compute this, then this, and then this. How many layers was that? 4. And then we had to come back up the chain. And how many layers did we go down? 1, 2, 3, 4. Yeah, it's not really returning a curly brace. This is just sort of how GDB is interpreting the recursion. Um, I think, to be honest, this will be a little bit more illuminating when we do this in assembly, because we will actually really see how recursion truly works. Okay, so give me a few weeks and right, then you guys will all be SOCAF, his eyes uncovered. No, SOCAF, his eyes uncovered. Oh, Shaka when the walls fell. It's a Star Trek reference. No, it's very much not a Fortnite reference. Okay. All right, so we can step through this, and then that curly brace is the end of the function, and then we're done. Okay. So inferior process exited normally. That's because we returned 0 to the operating system, and 0 is sort of the clean exit status. Okay. All right. So yeah, there's the sort of recursive the recursive version. All right, good question. What's going to happen if I put in a negative number, right? And you do have to kind of think about this as a programmer. What happens if your user is a complete idiot? Well, let me just run it. Okay, no, it's not going to like it. Okay, and the reason it's not going to like it, the error that's been generated here is called a segmentation fault. We'll talk more about what that means. Essentially, what's happened is the program has tried to access memory outside of its allocated memory segment that's been given to it by the operating system. And the reason that that happened is because, well, what would the program do if I put -4 in? What's it going to try and do? It's going to try and do -4 times -5, then times -6, and so on, because and each time it's going to subtract 1 and keep going, okay? And it's going to have to store all the values that it's dealt with previously in memory somewhere, okay? And on a stack or a heap or some other, but its point being, it's in memory someplace. Well, eventually, what's going to happen? Will this ever stop if I start with -6 or -4 rather? No, it won't. Okay. it will just keep going until eventually it runs out of memory. Or in this case, the operating system says, whoa, bro, I'm not giving you any more memory. Okay, but basically it runs out of memory. So the recursion cannot go on indefinitely. Now, does this mean that we, as the programmer and or the user, have been stupid? Yes. So how can we make this better and less stupid? Okay, if the number's negative, well, okay, you could do that. Or what about if we did something like, okay, ask and ye shall receive. Okay, yeah. Right? So this is obviously something that you as the programmer have to deal with, that you may get garbage data in from the user, or in this case, us being morons as the programmer. Yes, Owen. Yeah, that was Cole Borden's suggestion, right? You did? I did? Yeah, sure. Yeah, okay. So the first thing you have to do is put in a breakpoint, basically tell the thing, hey, run until you get to this point, okay? And so in this case, I wanted to just start at the very beginning of the program, which is the main routine. So the first thing I typed was break main.
When I do that, it says this.
Yes, that's fine. Now type run. And now step to go through the next.
Okay.
Yeah. Yeah, exactly. Okay. Now, like I said, if you're running this just from C and we compile directly to an executable with, of course, the debugging flag, this is sort of architecturally agnostic for our purposes right now. It won't matter really if you're doing this on whatever architecture, okay? This will matter when we get into the assembly, because GDB can do this with assembly also, where we'll literally step through line by line, but we'll be doing it with the assembly routines, not the C, okay? And I think when we first do this, you'll start to see, pun intended, how these things kind of line up together as much as possible. Yeah, you're welcome. Make sure to tip your waitress. What do you guys think? Cole, I think you're stupid. Yeah. Okay. All right. So, right. So the point, the lesson that we learned here is one that perhaps you guys had to deal with Python, is that always assume that your user is a complete idiot. Okay, and that they're going to do something to break your program. Okay. The other thing that would be stupid is, what about if I had, for example, put in a non-integer here for the number? Well, I would have a compiling error, and because I've declared it as an int. Okay, so I can't have an int of 4.7, for example. That doesn't make sense. However, if I use, and we'll talk about this function later, in Python, you guys probably did this a lot, where you accepted input from a user and they typed something and then you did something with it. right? So there is such a function in C to basically get console input from the user and then do something with it. And you have to worry about the format that it comes in as. Is it an int? Is it a floating point number? Is it a string? How do you deal with it from there? How long is that string? All of those sorts of things, okay? Okay, so, great. So let's write, we wrote this recursively. Let's write an iterative version, okay, of this that will output the exact same answer, but it's just going to do it in an iterative method instead of a recursive method, okay? And so what I mean by that is that we'll have a loop of some sort. We'll have a for loop, okay? Okay, so what's an iterative way of doing this? Let's say that I'm asked to compute 5 factorial. What will I do? All right, so okay, I need to have something like this. All right, let's have a base case just to catch ourselves. Well, sort of, but that's Python, right? Any brilliant ideas? Okay, for int I equals what? Okay, then what do you want to do next? Not quite. What are the 3 things that we need to start declaring a for loop? The initial value of a counting variable. What's next? Huh? Right, a termination condition or a continue looping condition, either way you want to think about it. And then the third thing that's required is whatever you do to your counting variable, which is usually incrementing or decrementing, okay? Now, because Caleb here said start with X, or sorry, yeah, because Broface started with X, okay, uh, started with X, right? Here I would be, instead of counting up, I'd rather count down, okay? So the way that I think about this is, let's say that I want to compute 5 factorial. Is 5 equal to 0? No. Okay, so we're in our positive case. Okay, so int I equals 5, I greater than 0, I minus minus. What I'm going to do is I'm going to take, I need to make a temporary variable, and I'll make it 1, okay, for reasons that'll become clear in a moment. Let me throw some space in here. And then I'm going to say temp equals temp times I. Okay? And then after the else case, I'm going to return temp. I did right there. Okay. And I defined its initial value to be 1 because what's 1 times anything? At first. That just, yeah, exactly. Okay. So let's run through this by hand. What's going to happen here? If I give this 4, Okay, what's the initial value of x? Okay, x is 4, temp is 1, because I defined it to be that. Okay, good? All right. Then I hit my for loop. What is the initial value of I? 4. Okay, I enter my loop body. Okay, so for int I equals 4, I greater than 0, I minus minus. Okay, so what's the first value of I? 4, okay? All right, temp equals temp times I. What's temp now? Temp equals equals 4. Okay, have I completed the loop body? Yes, and I need to go back and retest my continue/termination condition. What's I now? After I finish my loop body, what happens to the counting variable I? Huh? It's I minus minus is what I typed here in my loop. Okay, so what does I minus minus mean? Go down by 1, decrement. Okay, you can count upwards or downwards. In this case, only because Mr. Burge suggested that we start with int I equals x, are we counting down? Could we have counted up? Sure. Right, doesn't matter, right? There's more than one way to skin the cat, as we find out every November, except when there's a bad call and we get cheated out of a touchdown, right? Not that that may or may not have happened 2 years ago. Okay, anyway. All right, so I is 3, loop starts over. Is 3 bigger than 0? Yep, okay, so we continue. All right, so now what's temp? Currently it's 4. What's it going to be on this line? It'll be 4 times 3, which was our counting variable, which is 12. Okay, decrement I, is that bigger than 0? Yep. All right, so what's temp this time? 12 times 2. Okay. And then what's I now? Is that bigger than 0? Yeah. All right, so what's temp going to be on the next line? 24 times 1. Now, did we really need to compute that? Okay, so what could I have done here? Could I change this to I bigger than 1 without any consequence? Okay, do I get the same answer? Yes, because of course 1 times anything is itself, okay? But what that means is that I've only gone through the loop 1 fewer time. All right, saving 1 iteration is not really like all that critical in terms of execution time, but it's still 1 iteration. Okay, good? All right, so let's just make that little change. And then when all's said and done, we return our temp variable. Okay, good? All right, now let's compile it and run it and make sure everything's good. Oops. I can't call it fact 1. It's fact 2, okay? The other thing is, did we ever actually use it in our program here? No, okay. So let's do this. Let's change number back from our stupid case, okay? And then let's do this. Let's have it print both versions of the answer, the recursive version first and the iterative version second. And obviously, what should be the case? They should be the same thing, but let's make sure that they are. There we go. So we, of course, got the same answer. We just did it in two different ways. Okay, so Cole's question is, what happens if I delete this? Okay, what should happen? What do you guys think? Oh, did I forget to save it? Sorry. Oh, duh. Thanks. Oh, I thought I did. No, you haven't. And okay, so what's happened here is the printf function probably has a sort of stupid checker built into it. Okay, but what's up with that? Okay, well, so the way the printf function works, okay, is, and we'll talk about this, you pass it the location of a formatting string, okay, using a pointer. We'll talk about those more. And then you also pass it the location of data that it's going to plop into the different replacement spots. Well, if you're not careful about what data you tell it to print, and it just goes out into memory and finds whatever the hell happens to be there, then it's going to print just garbage. Okay, and that's what happened here, is it's printing garbage. Okay, this number, -75 whatever, just happened to be in memory. Okay. Well, no, but maybe think about it this way, right? Memory is just a crap ton of ones and zeros, right? And if you pick an arbitrary 32 bits of them, okay, and interpret that as an integer, it's actually a 50-50 chance that that thing is going to be a negative number, right? Because how would a 32-bit number be encoded? How do you know if the thing's negative or not? If the far left bit, the most significant bit, is a 1. Well, there's a 50-50 chance of that. So if you just pluck out some arbitrary 32 bits and think about it purely statistically, it's going to be 50-50 chance that that number appears as an integer to be a negative. Okay? But from our perspective, who cares what it is? It's garbage because it's not what we wanted. It's not our thing. In fact, I'm actually surprised GDB or the GCC compiled at all, because if I were writing a compiler, I would have been like, you've got 2% whatevers, you being stupid, because you're not passing things to them. Okay. And then we get, of course, our correct thing once I put them back. Okay. Okay, so that's the iterative version of this, or rather an iterative version of this, because I started counting down from the top rather than up from the bottom. Could we have done it both ways? Certainly, right? Just kind of which way do you want to think about it? All right, so let's just make sure we're all clear as to what the Fibonacci's are. Okay, what's the sequence? Starts with 2 1s, yes? 2. Okay, so what's the definition here? Okay, what's the recursion? Well, let me say it this way. I'll call F1 1, F2 1, and for n bigger than 2, Fn is, it's the sum of the previous two. Okay, Now, in this case, though, because it's defined in terms of a previous one and a previous one, the recursion is sort of double instead of a single layer, right? Whereas the factorial only depended on the one immediately preceding, okay? The other difference, of course, is that here it's addition rather than multiplication like it is in the factorial. Okay, whatever, right? That's just math. And this right here is the recursive definition, right? Okay, so if I asked you guys, which I will, to write a program like this that recursively and iteratively computes the nth, so let's say the 7th or 15th or some small number like that, Fibonacci number, recursively, what are we doing? We're doing that. What's the 7th Fibonacci number? It's the 6th one plus the 5th one. What's the 6th one? Well, it's the 5th one plus the 4th one, and so on. Okay, down to our base case, what's the 1st and the 2nd one? Those are both defined to be 1. Okay, so eventually you hit your base case in the same way. What were our base cases for the factorial? 0 factorial was 1, 1 factorial is 1. We could have instead said 2 factorial is 2 and had that be our base case, right? Because of course there's no need to multiply by 1, right? Because you know what you're going to get, or at least you better. Okay, so, right. Okay, so slightly difference there. And we could also iteratively compute these. I would go from the bottom up rather than the top down like we did here, but that'll be a good exercise, I think, for everybody, okay? So essentially, you're gonna write a program that kind of looks like what we did today, except instead of it being the factorial, it'll be the Fibonacci's, okay? You'll define a number, you'll compute the answer 2 different ways, you'll print it, and of course, A, you should get the same answer from both functions, and B, the factorial sequence is a known sequence, right? So you can look up and make sure that the 5th number is what it's supposed to be or whatever, okay? This is a very famous sequence. Now, where did this sequence come from, by the way, just for some brief bit of history? Yes, Leonardo of Pisa, better known as Fibonacci. It came as sort of a thought experiment for what happens if you have a bunch of breeding rabbits with unlimited food. Oh, and okay, I should also add, you have a bunch of breeding rabbits with an unlimited food supply, and you're also in Arkansas because there's some incest that goes on. Okay, right. And so if you start with one adult pair of rabbits and one baby pair of rabbits, then how many pairs of rabbits are you going to have after each successive generation? Well, initially, you have an adult pair of rabbits, they breed, there's still an adult pair of rabbits, but now, with a child pair of rabbits, and then it takes a cycle for the child rabbits to become adult rabbits, and now you have 2 pairs of adult rabbits, and the one is already pregnant from the last step, and so then you just kind of continue this going, right? So this sequence gets very big very fast, but yeah, it's breeding Arkansas bunnies. Unfortunately, Leonardo of Pisa did not know about Arkansas. So, anyway. Okay, so, good. So, we've got just a few minutes left. Let's start talking a little bit about strings, a little bit more about strings, and then we'll get into pointers later. So, a string, so let me just start a new example here. Well, Okay, so okay, so the way I declare a string is like this. Okay, so the brackety things are kind of like arrays in a sense, right? An array, a string is really just an array of characters, okay? And a character object in C is how many bits or bytes, depending which way you want to count. How are characters encoded in C? Well, that's how we represent it, but what's the actual encoding? Standard. ASCII, okay? ASCII is a what bit standard? How many bits does it take per character? Hmm? Come on, guys. Well, you can guess it's probably a power of 2 or a multiple of 2. Okay, yes, but which one is the correct answer in that pile? It's 8. 8 bits or 1 byte, okay? That's ASCII. Now, you want to do something in Unicode or UTF-8 or whatever, it's more, but for just regular old ASCII, it's 8 bits per character, okay? Or 1 byte. All right, so if I wanted to find a string of, let's say, 6 characters, then I can put a specific number there, okay? And then I could do, for example, well, let's see, hang on one second. Okay, my bad, I've got this backwards, hold on. Yeah, okay, so why was it backwards? What do you have to put first? Like with an int? The data type. What is the data type? Character, but really it's an array of characters, okay, as we'll see in a second. And so, for example, I can do something like my string 5 equals hello. All right, so let me delete this. Okay, and let's say that I want to print my string. I can have a format string, and that %s means string, and then I can do something like this. Okay? All right, good? All right, so let's compile it real quick. And we'll string 1. Okay, good? All right, now let's say that I'm a dumbass and I do something like this. Okay, why didn't it work? How many characters are in my string? 5. Okay, but I changed my number here to 4. Now, if I really had wanted to be careful here, what really should I have put there? I should have put 6, okay? Oops. And why? Because what does a string have to have at the end of it? Yeah, the null terminator, okay? So you got to be careful to make sure that you, and this will become more clear later, that the end of a string, the very last character should be 0, 0. okay? Because that's how you know that you've hit the end of a string, okay? All right, we'll talk more about that and pointers and stuff on Thursday, okay? All right, see you guys later.